What are we made of? It's one of the oldest questions we've ever asked. And just a little over a century ago, the answer everyone thought was right got completely blown out of the water. This is the story of how that happened. A story about a flawed theory, a brilliant student, and a single experiment that changed everything we know about the atom.
I love this proverb. It's all about a student who takes what their teacher taught them and just runs with it, surpassing them in brilliant ways. And that really sets the stage for our story, which is all about two giants of physics, J.J. Thomson and his one-time student, Ernest Rutherford. Okay, so to really get what Rutherford accomplished, we have to start with the theory he was actually testing. This was the cutting-edge science at the turn of the 20th century, and the best model of the atom came from his old mentor, J.J. Thomson.
So, Thomson had discovered the electron, which was huge, and to explain it, he came up with what we now call the plum pudding model. Just picture a ball of, well, pudding. This pudding is all positively charged, just spread out evenly. And then, scattered inside it, you've got these tiny negatively charged electrons, kind of like raisins. It all balances out, making the atom neutral.
Now, this model was pretty clever, right? It totally explained why atoms don't have a charge. But it left these two huge questions just hanging there. First off, how do you have positive and negative stuff all mixed together without them just, collapsing on each other? And second, electrons are super light. So what in the world makes up the rest of the atom's weight?
And it's exactly those questions that got Ernest Rutherford thinking. He decided to put his old mentor's model to the test. So in 1909, he designed what would become one of the most famous experiments in the history of science, all to get a peek inside that plum pudding atom.
The setup itself was so simple but brilliant. First, you've got a source that shoots out these tiny positive bullets called alpha particles. Then you aim that beam at a piece of gold foil that's been hammered so thin it's almost transparent. And finally, you wrap a detector screen around the whole thing, which would light up with a little flash every time a particle hit it. Simple. So, let's pause for a second. Before we get to the results, what do you think he expected to see? If the plum pudding model was right, what should have happened when those little alpha particles hit the gold? Well, according to the theory, the positive charge inside the gold atoms was all spread out, right? Kind of like a thin fog. So these heavy, fast-moving alpha particles should have just blasted right through it. The analogy they used was perfect. It should have been like firing a cannonball through a single sheet of tissue paper. Maybe a few particles get nudged a tiny bit, but that's it. They should all end up on the other side.
But that's not what happened. Not even close. What Rutherford and his team saw was so completely bizarre, so unexpected, it was about to rewrite physics. And the crazy thing is, at first, it looked like they were right. Almost all of the alpha particles did exactly what they were supposed to do. They flew straight through the foil and hit the detector on the far side. The tissue paper analogy seemed to be holding up just fine.
But then, they noticed something else, something that just shouldn't have been possible. For about every 20,000 particles that went through, one didn't.
A tiny fraction of these particles were deflected at wild angles. And some, that 1 in 20,000, came flying almost straight back at the source. The cannonball hadn't gone through the tissue paper. The tissue paper had somehow bounced the cannonball right back. This was absolutely impossible if the plum pudding model was correct.
Rutherford himself just couldn't believe it. He famously said it was as incredible as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. Something was fundamentally wrong with their picture of the atom.
But this unbelievable result, it wasn't a failure. It was the key. It was a clue that forced Rutherford to throw out the old model completely and come up with something radical, something new.
He thought it through, and it led him to 3 just brilliant conclusions. 1. Since most particles flew straight through, the atom has to be mostly empty space. 2. For something to bounce a heavy alpha particle back, all the atom's mass and positive charge must be packed into an incredibly small, dense center. And 3. That center must be positive to repel the positive alpha particles. He gave that center a name, the nucleus. And all of this led him to a brand new picture of the atom, the nuclear model. It's like a tiny solar system. You've got this small, heavy, positive nucleus right in the middle, and way out you have the light, negative electrons orbiting through all that empty space.
Rutherford's model was a massive success. It explained the experiment perfectly. But, and this is what's so cool about science, right? Every great answer just opens up a new,
even deeper question.
So on the one hand, his model was a huge win. It solved the mystery of the atom's mass and positive charge. But on the other hand, it created this massive new problem because it completely broke the known laws of physics.
Here's the thing. According to the physics of the time, classical electrodynamics, any charged particle moving in a circle, like an electron orbiting a nucleus, has to give off energy. And as it loses energy, it should slow down and spiral inwards, crashing into the nucleus in less than a second. According to the rulebook, every single atom in the universe should have collapsed instantly.
And that became the new, profound mystery. The experiment proved that the nucleus and electrons were there, but the laws of physics said they couldn't possibly be stable. So why doesn't it all just collapse? Well, answering that question would take a whole new type of physics and a trip into the very strange world of the quantum realm.